Hi everyone. In this video, we'll be discussing improper integrals. In particular, we'll revisit our definition of the definite integral. We'll develop the definition of improper integral to deal with cases where the definite integral does not apply. And we'll utilize integration techniques, the fundamental theorem of calculus, and limits to calculate improper integrals. So let's begin by sort of looking at two interesting questions. So both of these questions deal with the same function. They deal with the function 1 over x squared. And in the first problem, I want to know if I could find the area under the curve 1 over x squared that's to the right of the line x is equal to 1. In the second question, I want to ask, how could I find the area under the curve f of x is equal to 1 over x squared between x is equal to 0 and x is equal to 1? So first, let's think visually. What does this function look like, and what would these areas look like? So in the first case, here you see I have a function here. This is my function. This is my function f of x is equal to 1 over x squared. Okay, and you can see here I have my line x is equal to 1. Okay, so what I'm trying to find here is the area to the right of this line. That's this area here that's sort of in this yellow color. Okay, now the problem, of course, is that this function 1 over x squared has a horizontal asymptote at x is equal to 0. So this area sort of extends on and on and on and on all the way sort of out here towards infinity. So it's sort of a puzzling question. You might sort of immediately think, well, there's going to be an infinite amount of area there. But it's not exactly clear immediately how we might rigorously think about calculating that. But it is this area that we want to try and find here in that first problem, right? So my function f of x is 1 over x squared. This line x is equal to 1, and I'm looking there for the area to the right. You can already see sort of why these are called improper integrals, right? The notion of a definite integral often talks about finding the area under a curve between two values a and b. Here we have between some value a and like infinity. So you might somehow think of this as being something like the integral from 1 to infinity of f of x dx. Certainly, that's not our standard sort of definite integral. So there's already something sort of strange going on here that we're going to need to figure out how to take care of. Now, in the second question, right, we're asked to find the area between 0 and 1 of f of x. Now, if I just sort of were to write this down as an integral, you might think there's nothing particularly unusual about it. So but visually, you can sort of see what the issue is here. My function 1 over x squared is not defined at x is equal to 0. And in fact, it has a vertical asymptote at x is equal to 0. So again, we have the same sort of issue that it feels like our area is like running off to infinity somehow. But again, it's not clear how to make this work precisely. So right, the issue here really is that our function, and one of our assumptions about definite integrals when we defined them was that our function ought to be continuous on the closed interval a to b. And here this function 1 over x squared is not continuous on the closed interval 0 to 1. It has an infinite discontinuity at 0. So again, something sort of strange is going on here. And what we'd like to do is figure out how we might adapt our definition of the definite integral to help make sense of problems like this. All right, so in particular, for both of these, we've thought about expressing these as integrals. So this one is the integral from 1 to infinity of 1 over x squared dx. And here as the integral from 0 to 1 of 1 over x squared dx. Okay, and again, we've sort of already discussed this here. Our normal method doesn't work because our normal method of calculating a definite integral requires that these be real numbers, right? So like if this was 1 to 5, this would be no problem. but now I have 1 to infinity. So there's something improper about writing that. In this other example, I have the integral from 0 to 1. That looks okay. The issue I have, of course, is that this function 1 over x squared is not defined at x is equal to 0. So that's problematic and means that my normal notion of the definite integral won't work here. So I need to somehow adapt the methods that I have to try and make sense of problems like this. So let's see and think about how we might adapt each of these. So here's sort of an idea. In each case, what if I could approximate that that quantity that I'm trying to find, right, by a proper definite integral, and then take some sort of limit to recover the true value? So the idea here would be, if I want this integral from 1 to infinity of 1 over x squared, if I think about this, the problem here is really that sort of infinity piece. So what if I thought of this not as the integral from 1 to infinity, but as the integral from 1 to b of 1 over x squared dx, where I'm imagining now that b is some finite positive number. Now, if I then let this get large, so you sort of imagine if b goes to infinity, then maybe I would recover something like my original integral here. So what if, instead of just having this, what if I express this as the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx? Okay, that sort of seems reasonable. Now, for any fixed value of b, this quantity makes sense, right? Because this function is well-defined and continuous on the interval from 1 to any fixed value of b. Then I'll just let the limit part go to infinity. Okay. Similarly, down here, I have an issue at 0. So what if I replaced 0? Oh, I don't need to erase that yet. What if I replaced 0 with an a? So what if I took an integral from a to 1? And now what I want is I want a to be some value which is bigger than 0, but then I want to let all my a's go to 0. So I'm going to take a limit here as a goes to 0, but from above of 1 over x squared dx. Now again, this integral here, for any value of a greater than 0 and less than 1, actually any value greater than 0 will work, but in particular less than 1, this integral will be well defined because this function is continuous on the interval from a to 1 as long as a is greater than 0. So I can calculate this integral for any of those a values and then see what happens as I let a get closer and closer and closer to 0. Okay. Let's take a look at visually what that's doing. And in order to do that, we're actually going to switch over for a minute to Desmos. So I swap over here for a second. All right. So in this first case, I'm really thinking about that integral, the integral from 1 to b of 1 over x squared dx. Now, what you can see here is I have a slider for b. And so as I change that b, you can see that the value of this integral that's displaying right here, so that value of that integral is changing. So if I really want to know something about what happens as b goes to infinity, so I'm going to take a limit as b goes to infinity, right? Then I ought to let b just get larger and larger and larger and see what happens. Well, in this case, as I let b get larger and larger and larger, and keep dragging it, you can see that this is increasing, but it's sort of slowing down how quickly it's increasing. Now here we've only gone out to b is equal to, say, 11 right there. Okay, and so at b is equal to 11, my integral is about 0.9. Now, this is by no means a proof of anything, right? Possibly it keeps getting larger and larger and larger forever and ever and ever. But maybe to help convince you, if I actually pop out this piece here, I can actually make b as large as or very large. So maybe I let b go up to 1,000. And you'll see by the time b gets to 1,000, my integral is 0.99. And if I kept going, you would see that it really appears that this integral is approaching 1 as b gets larger and larger. So if I think that this is 1, then really the area under this curve then should be 1, because what I'm doing is I'm taking more and more and more of the area, and as I take more and more and more of the x-axis and calculate the area between 1 and that x value, the value of my integral is approaching 1. Let's then look at the other case as well to think about sort of geometrically what's going on there. So in the other case, here I'm looking at the limit as a approaches 0 from above of the integral from a to 1 of 1 over x squared dx. Sorry, I think maybe this very upper limit of integration cut off there. And so in this case, I'm taking this value a, and I'm going to drag it down closer and closer to 0 and see what happens to the value of my integral. And just to help view this a little better, let's blow it up a bit. Okay, so drag this value of a down, watch what happens to the value of my integral. Now, so far it sort of looks like the other one, although now it's already gotten bigger than 1. Okay, but it's not growing really, really quickly. But now watch what happens as I get closer and closer to 0. The value of my integral starts to grow faster and faster and faster. And you can see as I get closer and closer to 0, right now it's jumped up to 13. And if I can get it a little closer now, it's 32. Okay, and now here again, I can, if I come over here, I can actually maybe make this even a little bit smaller without getting, so when b is 0.001, you see the value of my integral is now 99. If I kept letting that value of a, get smaller and smaller, right, then what would happen is that integral, this limit here is going to get larger and larger. So here, as a goes to 0, the value of this integral is blowing up. And in fact, this limit is infinite. Okay. So going in this direction, I actually seem to have infinite area, whereas when I was going in the other direction, I seem to have finite area of 1. All right. So let's see if we can sort of formalize all of this and make sense of problems like this. So we now know, right, that this first integral seems like it should be something like 1, while this second integral seems like it's like infinite or something, right? So we want to figure out then how to sort of talk about these things. And in order to do this, we're going to break this up into two types of improper integrals. This will be sort of a representative of type 1. This will be a representative of type 2. So let's sort of define the different types of improper integrals we can have. So if your function f is continuous on a closed interval from a, some value a, up to infinity, then we can talk about the improper integral, which is the integral from a to infinity of f of x dx. So again, this is type 1 because it's improper because of this infinite limit of integration here. So we will define the value of this integral to be the limit as b goes to infinity of the integral from a to b of f of x dx, provided that the limit exists and is finite. Otherwise, we would say that this improper integral diverges. So in the case we saw a minute ago, we had the integral from 1 to infinity of 1 over x squared dx. This definition tells me that the way I should interpret this is I should interpret this as the limit as b goes to infinity of the integral from 1 to b of f of x dx, sorry, of 1 over x squared is my function here, dx. Now, because I'm thinking of b as being some finite value, which I'm then going to let go off to infinity, but for now it's a finite value, this is a perfectly well-defined definite integral, and I can use the fundamental theorem of calculus here. So this would be the limit as b goes to infinity of whatever the value of this integral is. Now, what I'm going to do is I'm going to go off to sort of the bottom here, and I'm going to do a little work to figure out what is this integral sitting here. Right? So if I look at this, let's see, the integral from 1 to b of 1 over x squared dx. I take an antiderivative of 1 over x squared, so that's just minus 1 over x. I evaluate it at b and 1 and take a difference. So that's minus 1 over b minus negative 1 over 1, or minus 1 over b plus 1. So now I can plug that back in up here. And what I see here is that the value of this improper integral ought to be equal to this limit. Now, as b goes to infinity, 1 over b will go to 0, right? As the denominator gets larger and larger, this 1 over b gets smaller and smaller, approaching 0. So this limit is just minus 0 plus 1, or 1. And so we say that this improper integral converges, and it converges to 1. Now, I'll also note that we can similarly deal with problems where we have an infinite limit of integration, but in the lower limit of integration. So imagine if instead we had the integral from minus infinity to b of f of x dx. Well, then we could just rewrite that. Now the improper limit of integration, right, is this lower limit of integration. And so we would just rewrite this as the limit as a goes to minus infinity of the integral from a to b of f of x dx. Again, if the limit exists and is finite, then we say this improper integral converges to that value. And if that integral does not exist or is not finite, then we would say the improper integral diverges. And we'll see more examples of that in a bit. All right. So let's go ahead and look at another example. Let's say we're asked to determine whether the improper integral converges or diverges, and we're given this integral, the integral from 3 to infinity of 1 over x natural log of x dx. Now, first we need to note, why is this an improper integral? It's an improper integral because I have an infinite limit of integration. And so in order to make any sense of this problem, the first thing I'm going to have to do is sort of rethink of this problem and reformulate it as the limit as b goes to infinity of the integral from 3 to infinity, or sorry, the integral from 3 to b of 1 over x natural log of x dx. Okay. Well, now I need to first make sense of this integral. Okay. So I'm going to come down here and say, okay, I would really like to know what the integral from 3 to b of 1 over x natural log of x is. Okay. And I may even, so now I know that I can use the fundamental theorem of calculus here, but I may want to break this down even further and say the first thing I'm going to need is an antiderivative of 1 over x natural log of x. So I may need to know first this antiderivative. So if I do this, the first thing I notice is that to compute this antiderivative, I need to do a u substitution. So if I let u be natural log of x, then du will be 1 over x dx. And so this will become the integral of 1 over u du. The antiderivative of 1 over u is natural log of u plus c. And u was simply natural log of x, so this becomes the natural log of x plus c. Well, now I need an antiderivative, so let me just choose c is equal to 0. And now in order to compute this definite integral, this will be natural log of x evaluated at b and 3 and take a difference. So this will be natural log of b minus natural log of 3. Now, this is the value of the integral from 3 to b. Now I need to plug that in back to my original formulation up here. I need to know what's the limit as b goes to infinity of natural log of b minus natural log of 3. Now, this is a constant as far as b is concerned. So really what I need to look at is this term. And I need to ask myself what happens to natural log of b as b goes off to infinity. So as b goes to infinity, natural log of b also goes to infinity. So if we just think about the graph of natural log 1, and my graph of natural log looks like this. Okay. And so if I think of this as b versus natural log of b, right? As b goes to infinity, natural log of b is also going to infinity. So this is going to go to infinity, but now you have a natural log of that, but natural log of something going to infinity is also going to infinity. And so what you get is that this, this limit, this term is going to infinity. You're subtracting off some finite amount, but that's whole limit is still going to infinity. And so you get that this improper integral diverges. Okay? So the integral diverges. So anytime you're dealing with these problems of an improper integral, the first step is to reformulate the problem as the limit of some definite integral. Then we need to calculate that definite integral, which we probably want to use the fundamental theorem of calculus on, which requires an antiderivative. So we may need to use some method of integration to help us find an antiderivative. Once we have that antiderivative, we can use that and the fundamental theorem of calculus to find the value of the definite integral. Once I have the value of the definite integral, that goes back in, and now I actually evaluate the limit to determine whether the improper integral converges or diverges. So note here it diverges because the integral was infinite. If we had computed this limit and gotten 4, then we would say that the improper integral converges and converges to 4. But in this case, it diverges because it was infinite. Let's look at another problem now, which presents some additional challenges. So let's say we were asked to determine whether this improper integral converges or diverges. The integral from minus infinity to infinity of x e to the minus x squared dx. Now, looking here, again, we could first ask, well, what's improper about this integral? And in some sense, this is worse than anything we've seen before, because now we have both negative infinity and positive infinity as limits of integration. And I don't really have a way for dealing with that. The two things we saw is sort of, well, what if the upper one's infinity? What if the lower one's negative infinity? But never, what do we do if they're both infinite at the same time? So, anytime we look at a problem and we see two weird things, we might want to isolate them so that we can deal with them sort of one by one. So in particular, in this case, I might first think about rewriting this integral so that if I rewrite it as two integrals, each of them only has one infinite limit of integration. So for example, I might break this up as an integral from minus infinity to 0 of x e to the minus x squared dx plus an integral from 0 to infinity of x e to the minus x squared dx. Now, the nice thing about this is while now I have two improper integrals, they're each sort of improper integrals that I know how to deal with. Okay, so I can sort of look at each of these and say, okay, right, this should be the limit as a goes to minus infinity of the integral from a to 0 of x e to the minus x squared dx. And this should be the limit as b goes to infinity of the integral from 0 to b of x e to the minus x squared dx. So I've taken sort of the two improper parts of this integral, and I've isolated each of them to sort of its own problem here. Okay, and so now I just need to compute these two things. Now, notice that these are going to end up being similar, right? Because I'm integrating the same function, right? Even though they're different definite integrals because I have different limits of integration. But the first thing I'm going to need to do is I'm going to need to find an antiderivative of this function. So what I'm going to do is I'm going to sort of wipe the board clean here, and I'm just going to give us a blank slate to sort of work the rest of this problem. Okay. So again, we have these two things, but the first thing we're going to need to do is we're going to need to find an antiderivative of x e to the minus x squared dx. And again, looking at this, I see a function minus x squared and almost its derivative. Its derivative up to multiplication by some constant, so probably u substitution would work here. So if u is minus x squared, then du would be minus 2x dx. And I just have an x dx, so probably need to bring this minus 2 over. So I'll divide both sides by minus 2. That'll give me a minus 1/2 du dx. Or sorry, minus 1/2 du is equal to x dx. And so this will become the integral minus 1/2 e to the u du. And its antiderivative, of course, would just be minus 1/2 e to the u plus c. But I have to remember that I made up u. U was minus x squared. So I end up with minus 1/2 e to the minus x squared plus c as my family of antiderivatives for the function x e to the minus x squared. Now, I'm going to need to evaluate both the integral from a to 0 of x e to the minus x squared dx. Separate my board here. And I'm also going to need to evaluate the integral from 0 to b of x e to the minus x squared dx. Now, for both of these, I can use the fundamental theorem of calculus. And I already have, well, all of my antiderivatives, and I just need one. So take c to be 0. So this should be minus 1/2 e to the minus x squared, evaluated at 0 and a, and take a difference. This should be minus 1/2 e to the minus x squared, evaluated at b and 0, and take a difference. So over here, evaluate at 0. If I evaluate at 0, I'm just going to get e to the 0, which is 1. So I'll just get minus 1/2. And then if I evaluate at a, so I'll minus, evaluating at a will give me minus 1/2 e to the minus a squared. And so what I end up with is minus 1/2 plus 1/2 e to the minus a squared. Over here, something similar happens, but I just need to, it's slightly different. So if I evaluate at b, I get a minus 1/2 e to the minus b squared. Minus, when I evaluate at 0, evaluating at 0 will give me minus 1/2, because e to the 0 will just be 1. And so I'll end up with minus 1/2 e to the minus b squared plus 1/2. But now I need to remember, I have to go back now and plug in. Here I'm going to take a limit as a goes to minus infinity. Here I'm going to take a limit as b goes to plus infinity. Okay, and I need to look at both of those carefully and see what happens. Okay, so let's erase this. So sort of going back to our original problem here, right? This is how I had rewritten each of these, and now I know these definite integrals. So this is equal to the limit as a goes to minus infinity, and now we computed this. This was 1/2 minus 1/2 e to the minus a squared. So that's just the value of that definite integral plugged in here, plus the limit as b goes to infinity of this definite integral, which we calculated, which was minus 1/2. Wait, sorry, I think I have a sign error somewhere here. And I erased what I wrote. So let's see, which one did I get wrong? So I plug in for limit of b would give me minus 1/2 e to the minus b squared, and then evaluated at 0 would give me minus that, so plus 1/2. So let's see, I think my error must be over here. When I plugged in 0, I would have gotten minus 1/2. And then when I plugged in minus negative, I would have gotten plus there. Okay, I think that should be right now. Okay. And so now when I evaluate each of these limits, as a goes to minus infinity, let's think about what's going to happen to this quantity. Well, I'm going to have minus 1/2. That's a constant with respect to a. That's not changing. But now I have this term. Okay, so let's think about what's happening. A is going to minus infinity, but the first thing that's happening to it is it's being squared. So when minus infinity is squared, like when you have a number, it's going to minus infinity, but then you are squaring it, that's now going to go to positive infinity, because when we square it, it's going to switch to positive. So now you have a squared is going to positive infinity. So minus a squared is now going to negative infinity. And now you have e raised to the power of something that's going to negative infinity. If I think about the graph of e to the x, the graph of e to the x looks like this, okay? And as your input goes to negative infinity, e to that input goes to 0. So the limit of this term is just 0. Okay? So that's the first two terms. Now these second two terms, a similar thing is going to happen here. As b goes to infinity, b squared goes to infinity. So minus b squared goes to minus infinity. E raised to the power of something going to minus infinity is going to go to 0. And so that's 0 plus 1/2. That's that term and that term. And now you end up with minus 1/2 plus 0 plus 0 plus positive 1/2. And it turns out here that this improper integral does converge. It converges to 0. And you might wonder sort of why does that happen, right? That might seem a little strange. And what I'd encourage you to do actually is to go graph the function. So if you were to graph the function x e to the minus x squared, What you would see actually is that it's what we call an odd function. And odd functions are what we call symmetric about the origin. So roughly, if I were to sketch a graph of this function, it looks something like this. Okay. And essentially what happens is that the amount of negative area over here balances out perfectly with the amount of positive area over here, and they end up canceling out so that you get 0 total signed area. Okay. But again, you go into Desmos or use a graphing calculator to check that out, and you'll get a better picture certainly than what I drew. But it might help you make sense a little bit more of why that area ought to be 0. But that improper integral does in fact converge. All right, so now that we've done a couple of examples, I think it's time for a knowledge check. So I want you to determine whether this improper integral converges or diverges. So this is the integral from -infinity to 0 of 1 over the square root of 4 minus x dx. So the video is going to pause. Take a moment to check, see if you can determine whether this integral converges or diverges. Okay, great. Let's see what you got. So in this case, the first thing we need to do is rewrite our integral. The improper bit here is this -infinity limit of integration. So we're going to rewrite this as the limit as a goes to -infinity of the integral from a to 0 of 1 over the square root of 4 minus x dx. So again, the first thing we need to do then is compute this definite integral, okay? And so I want to compute the integral from a to 0 of 1 over square root of 4 minus x dx. And again, the first thing I might want to do there then is compute the antiderivative of 1 over the square root of 4 minus x dx. Now, to help me a bit here, I might first rewrite the integrand. This is 4 minus x to the -1/2 power. Okay. And if I do, you can either sort of do this in your head and try to figure it out, or you can do sort of a mini u substitution here. So if you were to let u be 4 minus x, then du would just be -1 dx or minus dx. And so what you would end up with here after a u substitution would be minus the integral of u to the -1/2 du. And now this is just a power rule problem. So this is the minus we carry along. Now we increase the power by 1. So we get u to the 1/2. Divide by the new power. So divide by 1/2 is the same as multiplying by 2. So we get -2u to the 1/2, which is really -2 square root of u. But remember, I made up u, so this is really -2 square root of 4 minus x. All right. Oh, I should say, oops. Once I took the integrals here, right, these should all have a plus c. Okay. But now up here, I just need an antiderivative. So I'm going to choose c to be 0. So this integral should be the antiderivative 2 times square root of 4 minus x, evaluated at 0 and a, and take a difference. So if I evaluate at 0, I get 2 times the square root of 4 minus 0. Minus, if I evaluate at a, I get 2 square root of 4 minus a. And so what happens here is that 4 minus 0 is just 4. Square root of that is 2. 2 times 2 is 4. So I get 4 minus 2 square root of 4 minus a as the value of this definite integral. Now I need to plug that in up here and take a limit. So this is the limit as a goes to -infinity of 4 minus 2 square root of 4 minus a. All right. Well, now let's think about what's going to happen to this term as a goes to -infinity. So as a goes to minus infinity, 4 minus that thing going to minus infinity, this whole thing is going to go to positive infinity. So you're going to have 4 minus 2 times something going to positive infinity. So you're going to have 4 minus something going to infinity. This limit will be minus infinity. Therefore, this integral diverges. All right. So all of these examples have dealt with what we're calling type 1 improper integrals. Let's look at the other possible type of improper integral. So imagine now that you have a function f which is continuous on some interval a to b, but it's not necessarily, it is continuous at a, but it's not continuous at b, okay? Then the improper integral from a to b of f of x dx, we're going to define as the limit as t approaches b from below of the integral from a to t f of x dx, provided that limit exists and is finite. And otherwise, we'll say the improper integral diverges. To think about this example, well, actually, we'll come back to this in a second. Let's actually first look at the other case. So you could also think about the case where your function is continuous not on the entire closed interval ab, but it's just not continuous at a. So it's continuous everywhere between a and b, but not necessarily at a. And in that case, you can think about the integral from a to b, which is improper now because my function f is not continuous at a. We can think of this as the limit as t approaches a from above of the integral from t to b of f of x dx. Again, provided the limit exists and is finite. And again, if the limit doesn't exist or is not finite, then we would say that integral diverges. So let's think back to that other example we were looking at the beginning. So what if we were thinking about this? This is improper because this function is not continuous. It's not continuous because it's not defined at 0. Okay? And so what this definition says is, well, I can think of this as being the limit as t approaches 0 from above of the integral from t to 1 of 1 over x squared dx. Now, a couple of things I want to point out here. Since this is the lower limit of integration, I'm taking a limit from above. The reason is, if you think back to that picture we were looking at before, right? I know my function is continuous everywhere between 0 and 1. It's just not continuous at 0. So for any, say, value of t that I choose between 0 and 1, this definite integral will be well defined. Okay. So what I want to do is I want to choose t values that are above 0, but that are coming back down to 0. Okay, and so that's exactly what this does, right? I'm taking the limit as t approaches 0 from above. If I don't put that there, then I allow the possibility that t is over here. And if t is over here, I don't know, I mean, my function looks like this over here. I don't know how to compute this as a nice definite integral because it has this vertical asymptote in between here. It's not continuous on this integral. So the whole reason for choosing t to be approaching 0 from above is so that you can guarantee that this is a well-defined definite integral on that interval t to 1. All right. Well, now once we rewrite this, right? Now we can compute this. So we've already looked at this. So the antiderivative is minus 1 over x. And then we're going to evaluate that at 1 and t. This will be the limit as t approaches 0 from above of minus 1 over 1 minus negative 1 over t squared. So again, if I've sort of skipped some steps here, right? I've just computed this definite integral and plugged that value in there. And now what I can see is, well, what happens as t approaches 0 from above? So my t-values are positive, but approaching 0. Well, this value, so my denominator is going to be getting really, really small, approaching 0. So 1 over that really, really small thing is going to become really, really large. So this term is actually going to go to positive infinity. You're subtracting 1, but that doesn't do anything to stop something from going to infinity. And so this limit is infinite. Okay, and hence we would say that this improper integral diverges. Let's look at a couple of other examples. So back to the last knowledge check. This is actually the same function. I'm just realized here I left off a dx, so let's just write in a dx there. So imagine you want to determine whether this improper integral converges or diverges. Now, before we were looking at the integral from minus infinity to 0. But now we're looking at the integral from 0 to 4. The tricky thing about these sort of type 2 improper integrals is that if you're not sort of already thinking about them being improper integrals, they're easy to miss. So why is this improper? There's sort of nothing inherently wrong about the limits of integration. They're just regular numbers, right? The issue is that this function is discontinuous at x is equal to 4. When x is equal to 4, my denominator is 0, and this expression is undefined. So this is a type 2 improper integral because this function is not continuous when x is equal to 4. Okay, so the first thing I need to do then is I need to reformulate this as a limit. So here it's my upper limit of integration I'm going to replace. Okay, and so I'm going to rewrite this with the limit as t goes to, in this case, 4. Right, and since it's an upper limit of integration, I want to approach 4 from below. And then I want the integral from 0 to t of 1 over the square root of 4 minus x dx. Okay. Now, we can make use of some work we've already done. So if I want to calculate here the integral from 0 to t of 1 over the square root of 4 minus x dx, again, I get a little bit of savings because we've already calculated this. We've already calculated this antiderivative. So the antiderivative here is minus minus 2 square root of 4 minus x. And we're going to evaluate at t and 0. Take a difference. And so this will be minus 2 square root of 4 minus t minus negative 2 square root of 4 minus 0. As before, this term will simplify to a plus 4. I'll get minus 2 square root of 4 minus t plus 4. And now I can come back in and plug this into my problem up here. So this would be a limit then as t approaches 4 from below of minus 2 square root of 4 minus t plus 4. Now, what's going to happen as t approaches 4 from below? And this is where it's actually very important here that we approach 4 from below. Because since we're approaching 4 from below, that means my t-values are all smaller than 4, which means that is positive, which means this square root is defined. If we tried to approach from above, this wouldn't be defined for any t-values bigger than 4. But since we're approaching 4 from below, this limit is defined. And in fact, as we approach 4 from below, these values are going to be getting smaller and smaller and smaller, and they're going to be going to 0, in fact. So the limit of this first term is 0. This 4 is still 4. And so I get that the value of this improper integral, it converges because this limit exists, and it converges to the value of 4. So again here, I think the tricky thing about the type 2, in actually calculating them, that you calculate them essentially exactly the same way you do other types of improper integrals. You just rewrite them as an appropriate limit problem. The tricky part here is that if you're not already thinking about it, it's easy to miss that a given integral is improper, right? You might just look at this and go, well, that integral looks fine, right? I have normal limits of integration. But you have to be careful here to notice that your integral is not continuous here, and therefore you need to actually treat this as an improper integral. Now, we've now seen how we can sort of compute a bunch of these directly, but sometimes directly computing improper integrals by hand is hard, either because we don't know how to find a nice antiderivative, or the limits that we end up coming up with in order to calculate the improper integral are just really hard to deal with. So in those cases, we might want to be able to compare our integrals to simpler integrals. Now, there's a trade-off here. When we compare things, it allows me to say less. So for example, I'm 6'1", and if I told you that my brother was taller than me, that doesn't tell you how tall my brother is, but it does tell you sort of some lower bound on how tall he is, right? He's at least taller than 6'1", right? So there's a trade-off because we won't know maybe exact values of these integrals, but we might be able to say whether they converge or diverge based on comparing them to a simpler integral, right? So you might sort of say, well, okay, since Quinn is tall and his brother is taller than he is, I don't know exactly how tall his brother is, but since Quinn is tall, his brother must also be tall, right? So it's that sort of comparison of things. We won't be able to say quite as much, but we'll still be able to say something. So to give you some idea, you can imagine even if you're just sort of looking at these integrals, you might sort of say, that blue function looks sort of nicer than the orange function. And so I might want to know, like, whether or not one of these integrals converges or diverges. So let's say I want to know whether this orange integral, so let's say I'm going to take, say, the integral from 2, imagine I was going to take the integral here from 2 to infinity, and let's call this orange function f of x. Okay, so imagine I wanted to know something about this integral. But again, maybe it's really some weird function, and I don't know how to integrate it, right? But the blue function looks nicer. Okay, and so I might say, well, what if instead I looked at the integral of the blue function? Okay, so could look at, and let me call this blue function g of x. Okay. So I could instead look at the integral from 2 to infinity of g of x. And then I could wonder, well, what if I looked at the integral from 2 to infinity of g of x dx, and because it was easier to deal with, I could determine that this converged. Well, if that integral converged, then this integral must also converge, right? Because the area under the orange curve, if there's finite area under the blue curve, then there must also be finite area under the orange curve, right? There couldn't possibly be infinite area under the orange curve and then only be finite area under this larger curve g of x, right? So in that case, I could also say, well, since this is bigger than this and this converges, that must imply that this integral also converges, right? Now, I could flip the argument around also. What if maybe I wanted to know something about g, and for some reason f was easier to deal with? Okay. So what if I was able to look at the integral from 2 to infinity of f, and I were to look at it and I go, oh, this integral, I computed it and it diverges. Okay. Well, if there's infinite area under this orange curve, then that must mean that there's also infinite area under this bigger blue curve, right? So that would tell me that this integral has to diverge, right? So sometimes knowing something about one integral can indirectly tell you something about the other. Now, it doesn't always yield useful information, though, okay? So imagine instead that when you computed the integral from 2 to infinity of f, you computed this and you said, oh, this integral converges. Okay. Well, that would tell you that there's finite area under this orange curve. Does that guarantee you that there's only finite area under this blue g of x curve? Well, not necessarily, because you don't know sort of how much more area you're adding on top here. So here, in this case, it doesn't really tell us anything about this integral g of x. Okay. Likewise, if I were to tell you that I knew that the integral from 2 to infinity of g of x, diverged, could you conclude anything about the integral from 2 to infinity of f of x? Well, in that case, I would be telling you that there's infinite area under this blue curve and asking if there has to be infinite area under this orange curve. Well, you don't know, right? Because there's infinite area under this whole thing, but maybe this smaller one, maybe it only has finitely much area, and it's the difference here that's adding in the infinite amount of area. So again, going this other way, you don't quite know what's going to happen there. So we can summarize this fairly basic geometric notion in a theorem. Do some erasing. We'll write the theorem down. So suppose you have two functions, f of x and g of x, just like I had drawn before. And suppose you know that f of x and g of x, they should both be positive functions, but f of x is smaller than g of x on some interval a, b, where a or b or both could be infinite, right? So it could be from minus infinity to infinity. It could be from 2 to infinity. It could be from minus infinity to 3. But you just have some interval. If you know that the integral of the larger function converges, so if the integral from a to b of g of x converges, then the integral of the smaller function must also converge. Also, if you know that the integral of the smaller function diverges, that means the integral of the bigger function has to diverge. Okay. Now, again, there are cases here that are not addressed. If the smaller function converges, that doesn't tell you anything about the larger function. And if the larger function diverges, that doesn't tell you anything about the smaller function. But in these two cases, so I often sort of think of these in my head as if the larger function converges, then the smaller function must converge. And if the smaller function diverges, then the larger function must diverge. Okay. Let's see how this can be really helpful in determining whether improper integrals converge or diverge. So say you were asked to determine whether or not this integral converges or diverges. Now, if you tried to just sort of use the definition, you would rewrite this as the limit as b goes to infinity of the integral from 1 to b of 1 plus sine of x over x cubed dx. And at some point in that calculation, you would need to try and find an antiderivative for this. That's going to be a pretty tricky task. So maybe trying to go that way isn't going to be very helpful. But what you may be able to do is find a function that's either slightly bigger than this or slightly smaller than this that is easier to determine whether it converges or diverges, and then see what that tells you. Okay, so if I look at this, the x cubed in the denominator, that's not too bad. It's sort of this sine of x I don't really like. And so one of the first things I might note is that I could take this 1 plus sine of x, and that, let's see, sine of x, the biggest sine of x ever gets is 1. So this is always less than or equal to 2. So then 1 plus sine of x divided by x cubed should be less than 2 over x cubed. Again, it is important here that I'm working on the interval from 1 to infinity, so my x values are always positive, so I'm dividing both sides by a positive value. So now if I want to know something about the convergence of this function, I could look at this function instead. Okay, so let me actually sort of go off to the side and ask myself, okay, well, what can I say about the integral from 1 to infinity of 2 over x cubed dx? Well, the first thing I could do is I guess I could just factor this 2 out. Just look at this. And now this is a nice improper integral of the sort I should sort of be able to do. I'm going to sort of go through this a little quickly. So this would be 2 times, this would be the limit as b goes to infinity of the integral from 1 to b of 1 over x cubed dx. Okay. So you need to find an antiderivative of 1 over x cubed, or x to the negative 3. So you increase the power by 1, so that's x to the negative 2, divide by the new power, divided by negative 2. So this would be 2 times the limit as b goes to infinity of, now this would be, your antiderivative now is negative 1 over 2x squared. Okay, so it'd be negative 1 over 2b squared minus negative 1 over 2 1 squared. Now, what's interesting here is that the actual value I get here doesn't matter. I just need to know whether this is going to, this limit is going to exist and be finite, or whether it's going to go off to infinity. But it's not too hard to see here. As b goes to infinity, this whole term will go to 0. And so this will go to 1/2. And 2 times 1/2 will just be 1. Okay. But now this is the value of this integral. Okay. And what we know is that this function, 2 divided by x cubed, is bigger than this function. And so what that tells us is that the integral from 1 to infinity of 1 plus sine x over x cubed dx should be less than or equal to this integral from 1 to infinity of 2 over x cubed, which I now, dx, which I now know is finite. It's 1, but I don't actually care about the fact that it's 1. I care about the fact that it's finite. So since this is finite, since the bigger integral converges, the smaller integral must also converge. Okay. What does it converge to? I have no idea. I don't know that it's 1. I just actually know that it's less than or equal to 1, but it doesn't tell me anything about what it converges to. I guess I know this, since this thing is positive, this integral is also greater than or equal to 0. So I know that it converges to something between 0 and 1, but this doesn't tell me at all what it converges to, but I do know that it must converge to something. Okay. So here, it's sort of important to note, right, the directions just say determine whether it converges or diverges. It doesn't say if it converges, tell me what it converges to. That would be a much harder problem to solve. Okay. But I can say for sure that it converges by comparison to this integral, which I can directly determine converges. Now, it would be really nice, like, I've already seen several examples of these integrals that are like 1 over x to the sum power. It might be nice to just sort of have some baseline functions that you know either converge or diverge. And so what we want to do is sort of create a list of base functions that we can sort of quickly glance at and go, oh, okay, I know for a fact that that converges, or I know for a fact that that diverges. These will be helpful moving forward so that we don't have to every time compute some improper integral. So this chart here gives several helpful integrals for comparison. So you'll actually notice that the first two, and I'll come over here so you can see what I'm pointing at. So sort of the first two rows here They involve integrals of the form 1 over x to some power. So in the first row, we have integrals from 1 to infinity of 1 over x to the p. So we've actually seen two examples of those now, because we've seen the integral from 1 to infinity of 1 over x squared, and we've also just seen the integral from 1 to infinity of 1 over x cubed. If you will recall, both of those integrals converged. And it turns out that anytime you integrate something from 1 to infinity of the form 1 over x to the p, that will converge if the power p is bigger than 1, and it will diverge if the power p is less than or equal to 1. This is actually something that you can show directly just using the definition and integrating, but it's nice to just sort of have these for reference, right? So for example, if I am asked what happens to the integral from 1 to infinity of 1 over square root of x dx? Well, I look at that and I go, well, that's really 1 to infinity of 1 over x to the 1/2 dx. This power here is less than or equal to 1, so this diverges, right? Because my table here tells me that if I have the integral from 1 to infinity of 1 over x to the p, and my power p is less than or equal to 1, then that's going to diverge, okay? Now, the sort of strange thing is, if you switch from integrating from 1 to infinity, and you switch to integrating from 0 to 1, things actually flip around, okay? So if you look in that second column, sorry, the second row, right, if I have the integral from 0 to 1 of 1 over x to the p, that will converge if p is less than 1. So in this case, 1/2 is less than 1. So this integral actually converges, okay? If p is greater than or equal to 1, then it diverges, okay? The other one that can be handy from time to time is the one that's in this sort of last row. So if you have the integral from 0 to infinity of e to the ax dx, that will converge if your a is negative, and it will diverge if your a is positive or if it's 0, okay? So these are all really helpful integrals to sort of have for comparison. It sort of saves you quickly. Like anytime you're doing a problem, you could, for example, just tell me, you know, oh, I have the integral from 0 to 1 of 1 over x to the 5th. Since 5 is greater than or equal to 1, I know that diverges, right? You can just sort of use these facts moving forward. So let's put some of those into action, or some of these into action, and see how that can be helpful. So imagine I ask you to determine whether this improper integral converges or diverges. So I have the integral from 0 to infinity of e to the minus x squared dx. Now, again, you could try to go back to sort of our definition. You could rewrite this as the limit as b goes to infinity of the integral from 0 to b of e to the minus x squared dx. When you try to compute an antiderivative of this, you're going to have a big problem. And that big problem is that this function does not have an antiderivative that's expressible in terms of the elementary functions that you're used to. So that's not really going to help very much, okay? So we need then to do something a little bit different, okay? And so what I'm actually going to do here is I'm going to break this integral up. So I'm going to think of this as the integral, this integral from 0 to infinity. I'm actually going to break it up into an integral from 0 to 1 of e to the minus x squared dx plus an integral from 1 to infinity of e to the minus x squared dx. Okay. Now, this first piece, sorry, I just realized those sort of ran into each other. So this up a little bit, so move that down a bit, plus integral from 1 to infinity. This first integral, it's a definite integral. It's a normal, proper, definite integral. It has some value. I don't know what it is, but it has some value. So whether or not this thing converges or diverges isn't going to depend on this. It's going to depend on whether or not this is finite. Okay. Well, now if I look at this, I can use something to help me here. Now, in general, I know that if x is bigger than 1, greater than or equal to 1, in fact, then x squared is greater than or equal to x. Okay. So you can actually get this. If x is bigger than 1, then x is positive. You multiply both sides by x, you get x squared is greater than or equal to x. Now, if I negate both sides of this, I get that negative x squared is less than negative x. Remember, when you multiply both sides of an inequality by a negative, it flips the inequality. And now if I exponentiate both sides, right, I get that e to the minus x squared is less than or equal to e to the minus x. So what I know is that e to the minus x is bigger than e to the minus x squared when x is greater than or equal to 1. Well, on this interval, my x is greater than or equal to 1, right? Okay, so let's use that then. So then this integral on the left-hand side, it's less than or equal to whatever the value of this integral is, some finite number, plus the integral from 1 to infinity of e to the minus x dx. Now, my table told me something about the integral from 0 to infinity of e to the minus x. It told me that that converges because my coefficient here is negative. But it didn't say anything about 1 to x, or sorry, 1 to infinity. It just said 0 to infinity. But this function is positive, and if I add in more, that's only going to make things bigger. And now I know that this integral converges from my table from before. And so if I just quickly pop back over, that should overlay this. So right, the integral from this last row, the integral from 0 to infinity of e to the ax. Here my a is -1. Since a is less than 0, this converges, right? Okay, so now back over here, this integral converges. So this whole thing then converges because this is just some finite number added to whatever this finite quantity is. So this larger thing converges, and now this integral must also converge. So again, even though I have no idea what this converges to, I can say for sure that it does in fact converge, which is a really powerful thing actually. But you might think, well, it's a lot of things it could be, and that's true. But at least I know that it converges to some real number, right? I know that there is some answer out there. And so, for example, then trying to use a computer to estimate the value is actually would make sense, right? And so there are lots of numerical integration methods that you might then try to approximate the value of this integral, given that you know from your analysis of the problem that the integral actually converges. If you didn't know whether or not it converged, you might be worried about sort of throwing it into a computer because the computer will spit out a number to you, whether it's sort of actually a valid approximation of this or not. All right, let's look at one more example. Imagine you're asked to determine whether this improper integral converges or diverges. Now, there are actually ways here of explicitly computing an antiderivative of this. It actually involves a trig substitution, but first you have to do something down here that involves completing the square. We didn't really talk about that, but algebraically, you could do this. But if all I want to know is whether it converges or diverges, that seems like a lot of work. I might be able to use comparison to my advantage here. Okay. Now, what can be tricky here is it's helpful to know whether you think it converges or you think it diverges first. And you might say, well, how would I know that here? Well, generally sort of a good rule of thumb in math is that higher powers often sort of dominate the behavior of things. So when I look here in the denominator, there's an x squared and there's an x and there's a 10, but probably this x squared is going to dominate the behavior. So I sort of think, well, what would happen if I had 1 over the square root of x squared? Well, 1 over the square root of x squared, that would just be like 1 over x. 1 over x diverges whether we're going from 1 to infinity or 0 to 1. So I probably think that this diverges. Now, why is that helpful? Well, if I think that this diverges and I want to use comparison, then what I probably want to do is I want to try and find a function that is smaller than this and show that that smaller function diverges. And I already sort of have my guess for what that might be. Maybe I could do that with like 1 over x, right? Okay. So let's sort of see how we're gonna do this. So we have 1 over the square root of x squared minus 9x minus 10. Okay. Now let's see. I want to make this function smaller. Okay. So if I want to make this function smaller, then I could either make the top bigger, but the top's really nice. I sort of don't want to mess with that. Or if I want to make this smaller, I can make the top smaller, or I can make the bottom bigger, right? Making the denominator of a fraction larger will make the overall value smaller. Okay. So how can I make this bigger? Well, I'm subtracting off 9x here, and x is between 3 and infinity, so it's positive. So these are all subtractions. If I got rid of those subtractions, that would make the bottom larger. And so I can see that 1 over x is in fact less than or equal to this whole expression. Okay. And so since I know that this integral diverges, and that's important and here, I know that diverges, and I know that 1 over x is less than or equal to this expression, then this integral from 3 to infinity of 1 over square root x squared minus 9x minus 10 diverges by comparison. So again, I have no idea what the value of this integral is. If I really needed the explicit value, I'd have to go the more algebraic route to actually compute it. But if all I want to know is whether this converges or diverges, then this simple comparison test will help me do that. By the way, when I say simple comparison, I mean a comparison to a simpler function, right? The comparison test, doing the comparison itself can still be quite tricky. But once we do it, we actually sort of swap out and get to work with a much simpler improper integral. And in this case, one that we already know the behavior of. All right. So now to wrap up, it's time for a knowledge check. So here you're given 4 integrals. And what I'd like you to do is I'd like you to determine which of the following integrals converge. Okay. And in fact, there may be more than one. There is more than one. So take a moment. The video will pause. See if you can determine which of these integrals converge. Okay, great. Let's quickly take a look at these. I'm not going to fully work out all 4 of these, but I will give you sort of I'll give you the answers, and I'll also give you sort of the idea, sort of what you should be thinking of when trying to determine whether or not these integrals converge. So just quickly looking at these, the ones which converge are B and C. Okay. The other 2 diverge. And really the way, well, there are a couple of ways to think about these. One is that, in fact, you can actually compute all of these directly. So I would encourage you, if you want some extra practice to go through, you could calculate each of these directly. But you can also do some comparisons in every case. So in this case, what you ought to be thinking is that these are something like a 1 over square root of x. And in these cases, you ought to be thinking that these are something like a 1 over x squared. And in all cases, you can also do a comparison. So you can either compute these directly, or you can do comparisons to determine whether or not these converge or diverge. Okay. That concludes this video. In both the homework and quiz, you'll have chances to practice this. And as always, please reach out if you have any questions.